The Future History of Energy and Transportation. Documenting the paradigm shift from the era of oil and internal combustion to the era of robotics. By Julian Cox. Narrated by the author with the aid of an artificial intelligence. Chapter 15. Service and Systems Level Efficiency Explored. We touched on the basics such as miles saved through traffic-aware GPS routing at the head of the chapter, noting that a 10% saving of wasted miles impacts efficiency across the board. Incidentally, the latter point is the argument against inductive charging, that typically introduces a circa 10% additional charging loss. Directly equivalent to reducing vehicle-level efficiency by 10%, if contemplated system-wide, as well as introducing power limitations, limited charge rates, and some novel safety issues such as a potential to melt metallic debris in the absence of sophisticated detection of stray metallic objects that resonate with an inductive charging coil, but are not the target charge coil. The argument for inductive charging follows the premise that relief from attaching a physical charge connector represents a marketable labor efficiency as well as relief from the corner case where a user forgets to charge their vehicle. Relief from these inconveniences in return for a circa 10% increase in energy costs, and emissions depending upon source emissions intensity, is hardly an elegant solution. Note that system-wide induction losses can be somewhat mitigated by closing the air gap with automation, raising and maneuvering the inductive charge pad to meet and align concentrically with the adjoining charge pad aboard a car. A process not wholly dissimilar to automating the insertion of a near-lossless, very high-powered charge connector. Similarly, in-road charging follows the highly questionable premise that a valuable materials efficiency can be arrived at by reducing the requirement for battery range aboard vehicles. In addition to the aforementioned inductive losses, such a system naturally confines range-limited vehicles to a given radius around a local in-road charging grid, and trades materials efficiency, at least capital efficiency of materials in terms of reduced battery size, for a significant capital investment in infrastructure, plus road maintenance overhead, plus the cost and materials involved in installing induction coils in each vehicle, while likely presenting an intolerable safety hazard in the wild. Safety considerations would depend upon what unforeseen object cannot be successfully anticipated and excluded from resonating with the coils, perhaps a molten wedding band, necklace or bicycle frame. Not to mention the potential to destroy at least the electronics of road vehicles, should a high-power induction coil be activated in error under an incompatible vehicle. Lastly, road wear, cracks and potholes, exposing the power electronics to saline road water if not directly to curious pedestrians. Nevertheless, autonomous charging is a critical requirement of autonomous road fleets. Almost certainly a lower cost and more appropriate solution to implement than ground plus vehicle induction coils, and their associated power electronics, will be to reuse the sophisticated resources of a vehicle's autonomy suite that is fully available, while parked for charging, to donate high-value machine intelligence to inexpensive accessories, including a self-guided charge connector at its simplest, but ultimately to robotic accessories of any kind desirable. This train of thought speaks to why an autonomous electric vehicle, especially a pickup truck, could benefit from incorporating a power jack, data socket and mounting points for the installation of aftermarket accessories, for which a market may arise, and given such accessories, for example a self-loading arm, will add considerable additional abilities to vehicles to serve humans, with comparatively little additional cost of human input, it predictably will. Thus far, we have looked at reducing the question of efficiency down to fungible energy efficiency, materials efficiency and labor efficiency to deliver a passenger mile at scale. Now let us take a first forward look at the developments unfolding now and throughout the coming years as it applies to labor savings related to vehicle autonomy. At the limit, robotic controls, meaning full vehicle autonomy in conjunction with autonomous smart grids for anticipating demand, and for storing and routing electricity, will shortly be capable in theory, and increasingly so in practice, of eliminating human labor throughout road transport fleet operations, from energy capture to delivered passenger miles, with the likely exception of vehicle service and command centers and of course with the exception of labor allocated and attracted, to designing and building infrastructure, autonomous vehicles, general robotics and the value-added systems and services thereof. Naturally, the opportunity exists to remove the labor of a non-passenger from the system, the driver. Meaning a human that either does not wish to travel to a vehicle's destination, except to serve the requirements of fellow passengers who do, and/or to move goods. Also the case of a person who does wish to travel to the destination, but wishes to do so as a passenger instead of expending their time and attention focused on controlling the vehicle during the journey. There is more. The advent of machine vision-enabled, networked autonomous vehicles driving on public roads and off-road essentially heralds the advent of the era of robotics. Robots designed to operate remotely on this planet Earth. Robots that are agnostic to the task of carrying a driver or any passengers, and still other robots that are specialized to the exclusion of carrying passengers. The point of saying this is that the use case of carrying passengers is the first and most obviously valuable of many applications for road-going autonomy. Already there are efforts to produce driverless road sweepers whose primary task is of course to sweep roads. Similarly, driverless steamrollers and agricultural machinery. Vehicle autonomy is the first truly major advance of physical labor-saving robots in daily life since the advent of the automatic washing machine, and the trend can be expected to progress similarly to the development of diverse home automation and industrial robotics. In this case, beyond the initial use case of delivering passengers from curb to completing certain tasks the driver or passengers might have performed with a manually operated vehicle, on arrival at a job site. Time and labor savings on mundane grocery shopping would seem to be a natural calling for the driverless and passenger-less autonomous vehicle. This is a trivial warehouse automation and integration task, just an autonomous drive-through lane at Walmart. If Walmart, why not X? Few retailers would wish to design themselves out of accepting such trade, and specializing in it offers a path to savings that can be reflected in more competitive pricing of retail goods. At the limit, there is no technical reason why a machine vision-equipped autonomous vehicle cannot make qualitative shopping decisions. Which apples to accept or reject at an organic farm shop, or I think she'll look good in that dress. If the market desires such services to be developed, the capacity to deliver them is inbuilt. In this way, robotic passenger and goods vehicles capable of operating autonomously out in the wild is just an introduction to the potential for diversity of autonomous outdoor appliances that can be expected to grow to address the market for just about any function currently performed by specialized, operator-controlled machines engaged in transport and beyond. Naturally, an 18-wheeler car transporter delivering autonomous electric vehicles from factory to customers will itself be an autonomous EV in very short order. There is no reason not to do this, and in fact such a vehicle is well underway in development by Tesla. Essentially the same EV technology, same network, just a specialized large-scale chassis. The rest is software, some additional tools like a tail lift or hydraulic ramp, and then validation testing and approvals. While the opportunities to go upwards in scale from passenger vehicles to large trucks, shipping and aircraft is fascinating, the opportunities for going downwards in scale, from passenger vehicle to human scale, is mind-blowing. A very obvious commercial opportunity exists for extending the capabilities of autonomous electric vehicles within human environments. Not a passenger vehicle, but an autonomous passenger. A humanoid robot. One capable of sitting in a seat designed for humans, ready to continue a mission after an autonomous road vehicle has arrived at the roadside of its destination. For example, a human-scale and roughly or closely human-shaped, machine vision-enabled, possibly LiDAR-augmented, EV operating on the same OTA, over-the-air, network, that is suitable for navigating through human foot traffic and throughout the remaining gamut of man-made and natural environments, where people walk or sit. Including sitting in vehicles such as trains, planes, boats or cars. A kind of humanoid robot that is suitable for navigating an autonomous ride-sharing network, collaborating with autonomous road vehicles and other autonomous machines, is a combination that will work to automate mundane warehouse to desk and retail to refrigerator operations over various surfaces, while navigating elevators, doors and stairs and anything else designed for interaction with feet and hands and not road wheels. Arrive in the truck, pick the apples from the trees, fill the truck and deliver the apples to the store. Update. RoboCrop from Fieldwork Robotics, UK has a development stage, machine vision guided, fruit picking robot for picking raspberries. If this, why not the operation of any tool for which there is a market requirement? Arrive in the truck, jackhammer the road, build the house, perform the surgery and so on. If this, why not the operation of any tool built for hands, feet or both, for which there is a market requirement. In theory, a humanoid robot could automate the operation of any vehicle or machine built to be operated by humans. This may be economically practicable for heavy machinery. Naturally, facing off against a fighter jet piloted by an artificially intelligent humanoid robot could pose a major problem. As a method of retrofitting autonomy to large numbers of non-autonomous road vehicles, it is clearly overkill, assuming that minimal hardware-based efforts like AI have any merit, beyond human driver assistance, indeed if there is any merit at all in displacing humans to run out the mileage of low-value non-autonomous road vehicles. For some visual cues, consider a combination of the Yamaha SRI Motobot, a humanoid that can ride an ordinary high-performance motorcycle on a track, the Boston Dynamics Atlas bipedal humanoid and the Hanson Sophia, a facially expressive human interface. Update: early trials of such a device have already begun. In this instance, a LiDAR-augmented humanoid robot stowed and deployed via a dispenser in a van. The Ford-digit robot, from Ford Associate Agility Robotics. This is not very science fiction anymore, clearly. The autonomous passenger is just not that much of a stretch from the autonomous, networked, machine vision-enabled, passenger-carrying EV. Update: 2021. Tesla has announced a humanoid robot based on its autopilot software and full self-driving computer hardware platforms, in conjunction with its Dojo neural net training accelerator program. Same core autonomous EV technology, same network, specialized fit-for-purpose chassis and tools, sized and shaped as desired from very small to container ship plus and humanoid in between. The rest is software, validation testing and approvals. Naturally, any concern about strategic dependency upon oil to maintain the balance of world military power is readily assuaged. The combination described is clearly horrendously weaponizable to augment cruise missiles and drones in the prosecution of unmanned warfare to encompass ground vehicles and door-to-door urban combat. Technically, a low-latency, massively redundant, satellite-networked drone army of this nature is ripe to be flown and within minutes anywhere on Earth via a fleet of reusable ballistic missiles that can land, unload and take off again, and do so at a fraction of the cost and time penalty of dispatching a carrier group, even when accounting for laying down and defending solar and storage charging depots required for such an incursion. Like any major technological advance, a mechanized army based on this technology is not something a human-operated, oil and internal combustion mechanized force could reasonably be expected to repel militarily, any more than human-operated oil and internal combustion could be expected to defend against it commercially, in a civilian setting. The combined system-wide energy, materials and labor efficiencies are simply too great. Footnote: after all is said on the subject of efficiency in the context of physics and economics, an unresolved issue remains in the domain of linguistics. Meaning that while an efficient killing machine or an efficient rocket engine is well understood to describe something more effective at its task than its inefficient counterpart, an efficient vehicle can seem like something comparatively feeble. While from a physics standpoint the same is in fact true, all else being equal, of an efficient industrial process or an efficient vehicle, nevertheless, energy efficiency in common parlance has taken on overtones of doing more with less, or simply doing with less. Essentially conflating the term efficiency with economizing. We are very definitely discussing powerful technology indeed, with the ability to do more, not less, that has been hitherto possible with oil and internal combustion. Perhaps after all, this chapter should have been titled A Hierarchy of Effectiveness.